Okay, in this lecture, we are going to go over an example about binary logistic regression. Suppose you're a doctor and a patient walks into the clinic and you'd like to predict, will this person have a heart attack in the next year or no? So, yes or no. Or maybe in HR manager that is going to ask, will this new hire quit within 2 years or no? So, yes or no. So, we are going to predict whether the specific person is going to quit in 2 years, yes or no. Or a bank, will the customer is going to default on the loan, yes or no. So, we are talking about questions or yes or no questions, and the outcome is going to be one out of two answers, either yes or no. So, this is our response variable. So, the binary logistic regression is about we would like to predict the probability that an event is going to happen. And this event has only two possible outcomes. Two possible outcomes. Yes or no, success or failure. What else? Survived or died. In each stayed or left. Buy is not gonna buy. So these are binaries, all of them. So binary is just two categories. Two categories. So these are the things that we are going to predict. Binary outcomes. Binary outcomes. Because the outcomes or the response variable is categorical and contains only two categories, binary categories, then we are talking about logistic regression. And again, we are going to predict the likelihood or the probability that this is going to happen. That's why we are going to use the logistic regression. In this data set, the goal is to predict the heart attack. A person is going to have an heart attack or no based on some predictors. The predictors that we have is the age group, the gender. These are categorical variable, contains three categories. The gender, we have two categories, binary. We have the age, which is a continuous. This is in years. We have the cholesterol level, which is continuous, the total cholesterol. And this is a classification or a categorical variable, yes or no, if the cholesterol is high or no. But remember, these are connected, by the way. So in other words, we cannot use both of them in the same function because these are related 100%, correlated 100%. And this is the cholesterol, or this is the heart attack variable, yes or no. So we're going to use these predictors, and based on these predictors, is a person that has these features going to have a heart attack or no? Okay. So we're going to predict the heart attack using this data set, using these variables. And this is the dependent variable, is the response variable. It's binary, yes or no. 0 is the no, yes is the 1. We can do that. And the independent variables or the predictors are the rest others, or the covariates, we call them. These are the ones that we're going to use in our model. And maybe someone's going to ask, why don't we use linear regression? It's a long story, but linear regression output is always giving you numbers between negative infinity to positive infinity. But now we are predicting the likelihood, the probability. When you do the probability, when you predict the probability has to be between 0 and 1. Okay. This is just in short. That's why we use something called logit transformation to make this works. The next question that we'd like to answer is the assumptions. What are the assumptions of the logistic regressions? These are quite few, and you don't need to do lots of mathematical work here. Number one, the outcome is binary. This is clear because if the outcome is not binary, you cannot use binary logistic regression. Number two, the observations have to be independent. So these are separated, independent people. The third one, we don't have severe multicollinearity. This can be checked, generally speaking, just by finding the VIF or the plot among the predictors. Also, the sample size has to be We have to have big sample size. And this is in literature, we have many ideas about this, many different opinions about how large is that. Just follow the book in this, which is probably 10 to 20 events per one predictor. So if you have 5, then you have to have at least, let's say, 100, between 50 to 100 cases. Also, we assume that we don't have a severe or extreme outliers. So these are the assumptions. It's not just, at least we mention them. For the outliers, we just look at the extreme outliers. We're looking for what's so-called influential outliers. If there's something weird that distorts your estimates, you can take it out in this case or investigate it. Just do whatever. And before we start, the most important part here, we have to differentiate between the probability and the odds ratios. The binary logistic regression, we rely a lot on the odds ratio. And before we talk about the odds ratios, if we talk about the probability, for example, if I say that there's 75% a chance that it's going to rain tomorrow, how did we come up with this? It's just we divide number of success divided by the total number of the trials. This is the general definition of the probability. But the logistic regression things becomes indirectly. We don't use the probability immediately. We use something called odds. The odds, we divide the number of success not by the total number of the trials. No. Number of success divided number of the failures. Example. Suppose I have 100 patients. Okay. And we predict that 75 of them will recover. What is the probability of the recovery is obviously 75 divided by the total number of patients, which is 100, which is about 75% of people will be recovered. But what is the odds of recovery? In this case, we divided number of success divided by the number of failures. Number of people who are going to recover divided by number of people who will not recover, which is 75 divided by 25, which is a 3. 3 in the numerator. In the denominator, we have 1. So 3 over 1, or 3 to 1. What does it mean? For every 3 people who recover, we have 1 person doesn't recover. Does that make sense? And how we find the odds, or how we find the probability, there's a formula that connects the odds and the probabilities, which is the probability equals the odds divided by the odds plus 1. And the most important part we need from the odds is the odds ratio, the odds ratio. And how do we read the odds ratios? And what does it mean? The odds ratio is the number that we're going to report in the logistic regression. And the odds ratio compares the odds of the event in one group to the odds of the event in the reference group. Again, it compares the odds of it's 2 odds technically. We have 2 odds. The odds of the event in one group divided by the odds of the event in another group, which is it's going to be the reference group. So one odds divided by the another, right? For example, let me give this example, and we're going to see this right now, this cholesterol and heart attack example. Suppose that odds of a heart attack for people with high cholesterol are 0.12. So these are the odds of heart attack for people with high cholesterol. Odds of heart attack for people with high cholesterol is 0.12. And the odds for people with normal cholesterol are 0.10 or 1. What is the odds ratio? The odds ratio is 0.12 divided by 0.1, which is about 1.2. What does this mean? It means people with high cholesterol are 1.2 times more likely to have a heart attack than people with normal cholesterol, which is about 20% increase in risk, right? So the odds ratios, we have to know that. The odds ratios takes numbers. We have 3 cases. If the odds ratios are equal 1, so there is no effect. What does it mean? The groups are equally likely. If the odds ratio is greater than 1, then the event is more likely in this group versus the reference group. If the odd ratio less than 1, then the event is less likely in this group versus the reference. However, if we have an odd ratio less than 1, it's going to be not easy to be interpreted. So that what we do, we flip it. We just take 1 divided by this odd ratio, we get the inverse comparison. What does it mean? For example, suppose that the odd ratio is equal 0.5 for women compared to men. This is the same as saying the odd ratio is 1 divided by 0.5, which is 2 for men compared to women. The same information. But this is going to be easier to be interpreted. Now, at the beginning, what we're going to do in this example, I'm just going to follow exactly what the book did. So we're going to start with predicting the heart attack using only one predictor, which is the gender, okay? So this is my data. I'm going to go to tasks, utilities, binary logistic regression. My response variable is heart attack. We care about the people who are going to have heart attack, which is 1. The link function is going to be logit. We are going to use the logit transformation. And my predictor is going to be right now, the one I'm going to use to predict the heart attack is just the gender. It's the question that I'm asking here. Does the gender predict the likelihood of having a heart attack or no? This is the simple question. Does it matter? Is it female or male for a person to have a heart attack or no? So this is not a continuous variable. It's a classification. So this is a gender. Also, we're going to use not the coding for the reference coding. Then I'm going to go to the model, main effect only, selection. I'm not going to use any techniques of the selection methods. Options, nothing. So I'm going just to run this guy. Okay. So this is the output. And first of all, we are going to see the model information. And this model information tells you the just basic things like the response, the data set, the name of the data set. The response variable is the heart attack. The number of response levels is 2. It's binary. And the model is binary logit, the one that we use here. Optimization technique is Fisher's scoring. It's one of the mathematical models. We just don't care about this one. And how many observations do we have? 500. The one that we use, also 500. Also, we have the heart attack. We have 0 and 1. The values that it takes 0. 442. No heart attack. This is the yes. 58. The class level information, we have the female takes the value 1. The male takes the value 0, which is the reference category. Because this is alphabetical order. The last one comes in the alphabetical order, takes the value of 0, which is the reference category, okay? Then the model convergence status, this has to be satisfied, so we are good. So this is done, mathematically works. Then we comes to the idea of the model fit statistic. These are the AIC, SE, and -2 log L. We are looking for smaller values. The question is, how do you smaller? No, we cannot know until we compare this model with other models, okay? So you have to do a comparison, okay? So the fit statistics or the model fit statistics, we are just comparing these with other models to know what model is doing better than the others. The Schwarz, the SC is the one that probably is more reliable and that gives more simpler models, so people look at this measure, or AIC, it depends. Anyway, after that, so this is nothing to do with this right now. This one, we look at it when we do comparison between multiple models. The one that we start looking at is the testing global null hypothesis. This is the null look at beta equals 0, because you have one beta here, so beta is equal 0. In other words, gender does not have any impact or doesn't predict the likelihood of the heart attack. Gender has nothing to do with the probability of having a heart attack. This is the null hypothesis. This is the status quo, right? But we have many tests here. We have 3 different tests. Some text, they are saying that the likelihood ratio is the one that we rely. It's the most reliable one. Some bugs, some softwares, they use just WALT or score. If you look at all of them, they are statistically significant. Statistically significant. So we reject the null hypothesis. We reject the fact that the gender has nothing to do with the probability of heart attack. No, the gender predicts the variation, or it says something about the probability of the likelihood of having a heart attack. After that, so the model is significant. Then how many independent or predictors we have? We have only one, which is the gender. So if you look at the gender, we have 1 degree of freedom. This is the Wald chi-square, which is exactly the same as this guy. Okay, just we use the one which is Wald here, the chi-square. The p is significant. So the gender as whole is significant. Then we break it down into the equation. So it comes the equation here. And after that, so anyway, here the gender again is significant. And after that, the most important part is the odds ratio estimates. This is the one that we're going to focus and read. But the problem is the odds ratio is 0.372, and it's less than 1. In other words, again, we have a female versus male. So the female are less likely to have a heart attack than men, because this is less than 1. But the question, how would we read this one? This is a challenging to read it. So what we do, we are going to change the reference category to be female is going to take the value of 0. Then this number is going to be flipped because it's going to be 1 over this number, 1 divided by 0.372. This is going to be easy for us to be interpreted. So what I'm going to do, I'm going just to go to code and edit. Then I'm going to go to gender. Then I'm going to add ref equals female. Ref is a keyword in what's called in SAS. This has to be done. Equals F is female. Why I said F and it has to be between single or double quotations, because this is a categorical variable. Okay. So there's going to be F here. So it's going to be understood as a female. Then we are going to run this. So if you run this, you're going to see how these are flipped class level information. The female becomes 0. The male becomes 1. Nothing has been changed here. Nothing has been changed here. But here we have the male. This is the male. So this is the coefficient of the male. Okay. And this number has been changed. Now we have male versus female is 2.7 approximately. So men are about 2.67 times more likely to have heart attack than women. This is the interpretation is much easier than how we read the other way around. Again, male or men are about 2.7 times more likely to have a heart attack than women, which is I think it's a great deal, right? The other thing that we would like to look at is the last table. By the way, if you look at the confidence intervals, the confidence interval does not contain the 1. So it's always a greater than 1. It's always going to be above 1. So this is significant again. There's a proof of significance. The second or the last table we are going to look at is the value of C, which is the AUC, the area under the curve. This is something that we talk about in data mining, but this number, we are looking for this number to be above 0.7, let's say. It's not bad. It's good, 0.6. What does it mean? That this is much better than flipping the coin. So the model is about, okay, flipping the coin is 50%. So either going to be tail or head. Now you get 61%. So 61% is about 61% here. 61%, we're talking about that the model is doing better than flipping the coin. 60%, right? Or we are talking about the percent concordant, which is another measure that what happens here, we take every possible pair of people. One had a heart attack and one that doesn't. And the question is, did the model give the person who had the heart attack a higher predicted probability? If yes, the pair is concordant. If no, the pair is discordant. If tiny probabilities, we say tied. Okay. So you have higher than this, which is good. So this is good. So the model overall is nice. The C value is the AUC value is still not acceptable, is not above 70%. But overall, this is the first model we develop. Let's develop another model and do a continuous, what's so called a continuous predictor. Just let's enter a continuous predictor. So this is the heart attack. We care about the ones who are having heart attack. Now we have continuous variable, which is the cholesterol level. And I am going to run this, okay? The same information that we had before. The only new stuff that we have is the cholesterol level, right? And again, if you compare the world chi-square value is the same as the cholesterol level. Now we don't have a reference category because this is a continuous variable, right? It's significant. And we have an issue with the interpretation. Why? Because for every, this is above 1, it's slightly above 1. So for every 1 unit increase in cholesterol, the odds of heart attack increase by about 1%. Just how would I know, by the way? Just subtract 1 from this number, by the way. You're going to get 0.19. Multiply by 100, so you're going to get 1.9%. But cholesterol, we don't measure the cholesterol in real life by just increasing by 1 unit. The cholesterol is measured when we check if it's increased by 10 units, 5 units probably, or 20 units. So we should have a practical, meaningful unit of change. So what I'm going to do, I'm going to go to the code change. I'm going to create a new statement. I'm going to say units. And I am going to say cholesterol is equal to 10 units. Then I'm going to run this. Then I'm going to see another table down there. This makes sense. So subtract 1 from this, you're going to get about 0.212. Multiply by 100%, you're going to get 21%. What does this mean? It means a 21% increase in risk for every 10 units jump in the cholesterol. It's much more meaningful than before, right? Now, again, this is the C value. The AUC is about 66%. Still, we are getting a good model, a decent, better than flipping the coin. I give you a person. Is this person is going to have a heart attack? Flip the coin, yes or no. But now this model gives you, if you give me the features, if you give me his cholesterol level, I can tell you the likelihood that is going to have a so-called heart attack or no. But now let's build the full model. Let's go to the binary logistic regression and build the heart attack model. It's one logit function classification. I'm going to add the age group. I'm going to add the age group and the gender and the cholesterol high. Because I added cholesterol high, I'm not going to add cholesterol here because it's going to be redundant information, right? But what we are going to do, we are going to change the reference categories. These are all categories based on the reference encoding. So I'm going to edit this. Someone's going to tell me why you do that. I can run this and do it in a way that the numbers are readable, interpretable. Okay. So age group reference equals, I'm going to go to the data age group. This is going to be my reference. I'm going to copy this. Where is it? Here. Okay. Gender reference. Female. We know this, right? We know that female because we tried the male. It's going to be opposite. The cholesterol high, we're going to say the cholesterol is going to be the 0. Okay. The normal cholesterol. After that, I am going to run this. Again, why is that? Because we want the odd ratios to show increased risks. We are comparing higher risk groups to the baseline groups. Above 1. Number odd ratio has to be above 1. It's easier to talk about than ratios below 1, right? Okay, the same as before. The first table is the same. Second table is the same. Third table is the same. Now we come up to the fourth table. We have age group. We have 3 groups. My reference group is zeros. The second variable, which is the female versus male, the design is 0, the reference. The cholesterol high, the 0 is the normal. and it's the reference. We are happy with the model. These are the model fit statistics. You can do a comparison now between this model, by the way, and other models using the AIC or SC and others, right? Next, we're going to look at the testing global null hypothesis. All of the betas are zeros, or at least one of them is not zero. In this case, we say the model is significant, so at least one of them is not zero. Now, how to do that, how to see which one is not zero, all of them are not zeros. So all of them is going to contribute to know or to have an effect on the likelihood of the heart attack. They're going to predict the likelihood of the heart attack. So all of them significant. Age group, gender, cholesterol high compared to the reference categories. And the detail, this is over, okay, this give you overall, this one give you the overall age group, okay? The overall age group. Now the question is, what about the next table, right? The next table is going to give you the details again. The next table is the one that we are going to use in the equation. Okay? So this is the intercept, and all of them are significant. Age group, this is significant, all of them are significant, okay? And all of these coefficients will appear in the equation. Then the most important part is the odds ratios estimate, okay? And the question is how to interpret these, which is as we did before. For interpreting this, let me just say something about these two things because it's important. The analysis of effects here, the type 3, it tests whether each variable as a whole contribute to the model significantly. So age group, for instance, contributes significantly to the model. So we have one p-value here. And we have 2 degree of freedom because we have 3 categories here. The reference plus the 2 dummy variables. So what we're asking here, does the age group overall matter or no? Then here, this give you, as I said, the coefficients, the estimates of the betas, and it tests each individual parameter or level. So for categorical variables with more than 2, we get a separate rows, as we see, age group for this group, for that group, right? So it appears twice in 2 rows. And these are tested, as I said, separately against the reference category. Does that make sense? So the last thing to do is to look at these estimates. This is 3.9. So people who are above or between 60 to 70, right, are about 3.9 times more likely to have heart attack than the people under 60, the reference category. The second one, the people over 70 are about, 7.1 more times to have a heart attack than people under 60. And this makes sense, kind of logically speaking. For the male and female, we talked about this. Men are about 2.9 times more likely to have heart attack than women. And the last one is people with high cholesterol versus the one. Remember, one is normal. People with high cholesterol are about 3.5 times more likely to have heart attack than those with normal cholesterol. And this model is really good. It's about 76% is the AUS is about 70. It's about 76%. It's really high. It's good. It's acceptable. It's acceptable. Isn't excellent. Fine. But look at the concordant is about 72. It was 66, right? So it's doing much better job compared to others. And yeah, so this is the whole thing about the logistic regression and how we interpret the odds ratios. If you find that some of them is less than one, whatever, you just change the reference category from the code, right? From the code, then run the model again. So this is about logistic regression. And yep, thank you.